Hello, everyone. My name is Lin Chen from University of Alberta. Today, it's my pleasure to show a presentation on the formation of Beany flavor in pea protein and the mitigation strategies. With the world population increase to 10 billion by 2050, we will need to have more proteins to support the growing population. Especially the plant protein global market will continuously to increase because plant-based protein, they have much land efficiency and they will generate much less greenhouse gas. And this has brought significant opportunities to crop resources in Canada, like soya and mustard in eastern of Canada, like pulses, canola, cereals in west of Canada. Especially, I would like to highlight pulses like pea, lentil, chickpea, faba bean. They are, not just a crop with high protein and high nutritive value, but they are also sustainable rotational crops because their root can fix nitrogen to the soil to increase the soil fertility. And the Canadian government has invested significantly in the plant protein industry to position Canada as the world supplier of high quality plant protein ingredient and plant-based food to support the growing population. Canada's food guide also address consumption of plant-based protein food because plant protein consumption is associated with a lower risk of chronic disease such as cardiovascular disease, obesity, and diabetes. Currently, in this plant protein space, soya protein is the leader and pea protein is catching up because it's not regarded as a major allergen and it has non-GMO status. This gives food industry an advantage to have final food product with clean label. Eventually, the pea has become one of the most commonly used protein source for food industry in the short to medium term. However, the texture and the flavor are important aspects that need improvement to increase pea protein market penetration. Especially the flavor in pea, normally labeled as Beany, influence the overall acceptance of pea protein-based food product. So today, I'm going to discuss about this Beany flavor, where they come from and what's the formation mechanisms. And from there, we are going to discuss the mitigation strategies. A recent paper by Shang and co-authors published in Bioscience is an excellent review to understand the Beany flavor in pea protein. Specifically, you can see the figure on the left side of the screen. It's a network relation plot of Beany flavor compounds and the corresponding order description. You can see the green nodes. They are the description of different flavors like earthy, fatty, green, mushroom. And then you can see the nodes with other colors. They are corresponding to different volatile compounds like aldehyde, ketone, and alcohols. Actually, there are a lot of volatile compounds identified in pea protein. The table on the right side lists 44 of them. And you can see the lines connecting these nodes. These show their correlations. So from here, this figure, you can see the Beany flavor is not a particular component, but rather is a combination effect of many flavor components together that create a Beany flavor. If we look at those nodes, green nodes with larger size, that means they are correlated with more volatile component, like the green vegetable, earthy, fatty, and mushroom flavor. Actually, the combination of them turn out to be the cause that contribute to the overall Beany flavor. And then specifically, if you look at the volatile component like aldehyde, ketones, and alcohols, they are the major volatile component identified in pea protein. Here, especially aldehyde, it's a volatile component, play a very important role to contribute to the Beany flavor because they have very low odor threshold. That's the lowest the concentration of the flavor can be perceived. For example, hexanol is one of the important aldehyde, and it has odor threshold of 4.1 ppb. That with tiny, tiny amount, you can smell it. Certainly, you have alcohols generated in the pea protein. However, they have much higher odor threshold. For example, like alcohols have the odor threshold 500 times larger than aldehyde. So alcohols, they have less important role to contribute to the Beany flavor. Since aldehyde is very important, so then this gives the question, where aldehyde come from, right? So this slide shows the mechanisms of the aldehyde generation in the pea protein. Actually, this is generated through the pea processing or protein extraction. We can see on the left side, you have the mechanism description. We have some polyunsaturated fatty acid in pea, like linoleic acid or alpha-linolenic acid. And those fatty acids, due to their unsaturated structures, they are prone to oxidation. So when you get started to have your processing, like you have the water added in the pea, then your lipogenase will get inactivated. This is the enzymes that specifically catalyze the oxidation of polyunsaturated fatty acid. And then once we call them LOX, represent the lipogenase. Once they get activated, they will interact with this polyunsaturated fatty acid. As an outcome, they will generate a lot of hydrogen peroxide derivatives, and then many of them will finally generate a hexanol as important aldehyde with very low odor threshold. Certainly, there are other enzymes that play a role, like hydroperoxide lyase, but lipogenase play a significant role. So you can see here, basically, there are aldehyde generated through the food processing and protein extraction. There's other aldehyde, in addition to hexanol, they can also form through this oxidation of polyunsaturated fatty acid. This can be catalyzed by LOX or through auto-oxidation without involvement of any enzyme. And then another volatile component that contributes to the Beany flavor is pyrazine. Pyrazine, this slide shows the structure of the pyrazine. Normally, they give their green and earthy flavor, and they have also very low odor threshold. Pyrazine actually is naturally present in very small amount in the raw pea. However, that small amount will not dominate the overall flavor. You have majority of the pyrazine also generated during the pea processing and the protein extraction. So when you get started to do the milling, you break the tissue structures, and then the protein will encounter the reducing sugar to have Maillard reaction. And then during the heating processing, like roasting, drying, or extrusion, the product from Maillard reaction will have stacker degradation to generate those pyrazines. So you can see the main volatile component that contribute to Beany flavor are produced during the process and end up concentrated in pea protein. Actually, for most proteins, they don't have a flavor. However, they can bind to the flavor component. Those binding are mainly based on their physical interactions. For example, if you have pea protein powder, the flavor can bind on those powders via one of our forces, hydrogen bonding. But if you have a liquid protein like protein in the solutions or the protein in the meta-analog in the moisture environment, the flavor binding will mainly based on hydrophobic interactions. On the right side of the slide, I have one figure to show aldehyde is the volatile component that contributed to Beany flavor. They have part of the molecule which is very hydrophobic. So they can bind with protein based on the hydrophobic pocket on the protein involving tryptophan or leucine. These are the hydrophobic amino acid together. So then normally the higher hydrophobic of those flavor compound, they have more interactions with the protein. So based on that, their hydrophobicity, the binding strands follow the sequence of aldehyde, ketone, and alcohol. So that's why aldehyde not only have very low water threshold, but also have very strong binding with the protein. So this is the most important component contributing to Beany flavor. Many of those interactions are physical interaction, as mentioned, so they are reversible. So industry practice, for example, like in soya industry, when they make soya-based milk, they will have heating processing to break those interactions. So then volatile compound will be released and get removed gradually from their soya protein. However, some of this compound can develop their covalent bonding with pea protein. For example, aldehyde, they can covalently bond to lysine, or some other off-flavor compound can bind to sulfur hydroxy group that is available in cysteine. So you can see the protein specifically high in lysine or cysteine arginine. They tend to have higher binding of their flavor, and the pea protein is one of them because pea protein has high lysine inside. Lysine is important, is an essential amino acid that increase the nutritive value of the pea protein, but also contribute to their binding of the flavor ingredient. And those covalent binding, once they are formed, they are irreversible, so they are important. Based on this understanding of the formation mechanisms of Beany flavor, we can see they are generally, produced during the processing catalyzed by lipogenase. And also eventually they bind with the protein to get a concentrated there. And also the volatile compound with low odor threshold like aldehyde, pyrazine, they have substantial role to the perceived Beany flavor. So based on this understanding, it's important for us to consider the mitigation strategies. So then the question is that can we remove lipogenase from pea? Or if we cannot remove them, can we inactivate, because it's enzyme, can we inactivate lipogenase in the pea? And also, if we have those volatile components generated, can we block their interaction with the protein so they can be removed by some processing, not accumulated in the protein? Or you have to have this volatile component. We know those aldehyde with low odor threshold, they are contributed to Beany flavor. So then do you have any way to convert those volatile component with low odor threshold into the component with high threshold? So then you have they have less chance to get perceived by our nose. So these are the considerations. And then based on that, we are going to discuss some of the mitigation strategies in the next step. Firstly, can we remove lipogenase? Actually, breeding is one of the way that is working. Those breeding work mainly happened in soya at this moment, with the focus to have the breeding of lipogenase-free genotypes. Their way they can decrease the chance of oxidation of unsaturated fatty acid, then can remove their Beany flavor. So there are some, soya genotypes commercialized in the United States, like NRC 132. The research demonstrate using those genotypes, their soya milk has much reduced off flavor. There are other lipogenase-free soybean genotypes are also in the pipeline. In Australia, there are also some lipoxygenase free lines, and research demonstrate use those genotypes, and they will have better sensory for soya milk and tofu products. So currently, according to literature review, I haven't seen any report on lipoxygenase-free genotypes for pea. However, there's a report that there's a mutant line of pea was identified that lack the seed lipoxygenase. This is the research reported in 1999. So there's a good chance with this, mutant line, through the breeding work, we may come up with some lipoxygenase-free genotypes for pea. So that's one of the direction I think the breeders should work towards. Recently, I found one paper. They use this gene editing work. This is more advanced technology. Got awarded with Nobel Prize in 2020 with this precision gene editing. You can make a lot of wonderful things. So this is a work as a collaborative work with NRC together, University of Manitoba, University of Saskatchewan. Basically using this gene editing work, they generate gene edited lines that show significantly reduced lipoxygenase activity. And also their hexanol as the key volatile component get 90% of the reduction. So possibly more work needed to required in this field to further test those, gene edited the pea to see when you make them into pea-based milk or pea-based tofu, whether the Beany flavor will be significantly reduced. This is gene editing work. In some jurisdictions, basically the regulatory framework for gene edited crops maybe have less stringent than for traditional GMO technology. Because in Canada, our pea is claimed with no GMO. And this new technology, they have precision control of the gene modification. And also they don't bring foreign DNA. Instead, they lock out some DNA. So hopefully in that way, this will allow the crop to bypass certain GMO regulatory hurdles. So we will see hopefully to see more development towards this direction. And also, I see some work in the European countries. They use more traditional breeding. They test the different varieties of the pea. And what they do is that they have the protein extracted from those pea grains by wet extraction method. And then they evaluated the sensory quality of those extracted pea protein by sensory panel. They identified some varieties they were perceived to have least pea-like flavor, and some varieties they were perceived to have higher pea-like flavor. So this will indicate that look at a large pool of genotypes of the pea, we may be able to find some genotypes that has lower Beany flavor. And also need to understand the mechanism behind that. In this research specifically, they found some moderate correlation between the pea-like flavor with lipoxygenase activity in these different genotypes. So that means there are other mechanisms happening there, but this is interesting work worthy of further investigation. In addition to breeding work or gene editing work, there are other research efforts. They try to inactivate hypoxygenase through thermal or non-thermal technique. The research demonstrate compared to the conventional heating, those innovative heating methods like radio frequency or non-thermal processing like pulse electric field, they are more effective to inactivate lipoxygenase. For example, with heating, you can have only 3% reduction due to the slow speed of heat conduction. However, if you use radio frequency heating, with 5 minutes of treatment, you can have lipogenase activity reduced by 93%, and you also have hexanol concentration significantly reduced. Also, the pulse electric field, with very short time of treatment, they can inactivate 88% of lipogenase. Those kind of efficient inhibition of lipogenase within a short period of time could be very significant, because the prolonged heating will get the protein denatured. That will lead to reduce the protein solubility or functional properties. However, if we use those novel technology, we can have the chance to activate lipogenase with minimum impact on the protein or other nutritive component in pea. There's also ideas that combine different technology together. For example, if we heat pea at 50 degrees, the temperature is not sufficient to inactivate lipogenase. However, if you have a pre-treatment of high pressure processing to change the crop tissue structures, then followed by 50 degrees of blanching for 30 minutes, you can have 70% of inactivation of lipogenase. So this is important to keep in mind. You need to still maintain the protein functional properties and the native structures. For example, some considerations that the non-thermal inactivation of lipogenase should carry it before pea is even processed. So in that way, you just inactivate lipogenase without trigger other undesirable reactions. So then you have the pea treated, and then after that, you start to have a milling of and protein extraction. Many of this work demonstrate they can very effectively inactivate lipogenase. However, analysis of the volatile component and the sensory quality of those proteins needed to be further investigated. This will truly demonstrate, with this evidence, you will demonstrate that those technology really can improve the flavor and reduce the Beany flavor from pea protein. So then these are the strategy one. There's other strategies I wanted to share with you. Strategy two is interfere with the protein binding of the flavor component. In this research, they use beta-cyclodextrin. It's a food ingredient derived from starch hydrolysis. If you see the figure, they have quite interesting structures with hydrophobic cavity inside. And those cavity will be able to hold volatile component that contribute to Beany flavor, because like aldehyde is also very hydrophobic. So specifically in this work, after alkaline extraction of the protein, they have cold spray drying of pea protein with beta-cyclodextrin. This will have the Beany flavor entrapped in this beta-cyclodextrin cage. This will lead to lower amount of aromatic component that can be perceived by the consumers. With very small amount of beta-cyclodextrin during the cold spray drying, they can reduce the volatile component, for example, to non by 94%. So this is one consideration to be considered. And also, there's other ways. For example, some research demonstrate that, yes, protein with high lysine, like pea protein, tend to have high flavor binding due to covalent interactions. So then they use enzyme transglutaminase to catalyze the binding of good flavor like vanilla and maltose with the protein. And those good flavor will compete with Beany flavor for the lysine binding site. So in that way, hopefully in this work, they can provide a way to increase the good flavor and prevent the binding of Beany flavor. So that's another strategy. So those strategies can be combined with thermal, non-thermal processing. You have thermal, non-thermal processing at the beginning, and then once you have the protein extract, you can have them to, spray dried with cyclodextrin, or you can add favorable flavor inside. And then there's also some chemical ways. For example, you can use hexane or alcohol to wash the Beany flavor compound away. This is effective. However, there are some limitations because when you remove those Beany flavor, you also have food flavor get washed, so the food become lighter in terms of the flavor and the taste. Another thing is that industry will need to have explosion-proof equipment and the facility to work on the organic solvent. That will significantly increase the cost of the processing. So some industry, they are reluctant to take this strategy. And then I will introduce the last one. So when we have to volatile component generated, can we convert those components with low threshold to those with high threshold? So then we have the biological method like fermentation that take a role. Like microorganisms, lactic acid bacteria or yeast or fungi, they can generate some enzymes like ADH. It stands for alcohol dehydrogenase, or ALDH is aldehyde dehydrogenase. Those are the enzymes abundant in those microorganisms. So what they do is that, for example, ADH, they can convert hexanol as an important aldehyde with low order threshold into alcohol or into some acid with much higher order threshold. So in this way, they can, remove the Beany flavor from pea protein. Also, research demonstrated through this fermentation, the microorganisms will generate some new aromatic component favorable, like mushroom, meaty, honey flavor. So in this way, generally, the fermentation is a promising method for obtaining positive aromal compound and reduce Beany flavor. There's many other transformation pathways during the fermentation, like can we have fermentation to remove pyrazine as another important volatile component in Beany flavor. In this methodology, the selection of the suitable microorganisms and the control of the fermentation conditions could be very important. It's important that you control also the fermentation time, as excessive fermentation time may affect the physical and the chemical properties of the protein. Because in the fermentation, you will have those protein get hydrolyzed or change from the protein into the fragment. So on one hand, they can increase the digestibility and the protein absorption. On the other hand, if the company don't want to have hydrolyzed the protein, then you may not choose the fermentation strategy. And towards the end, I wanted to mention that the storage condition is also very important. Those unsaturated fat or volatile component can be removed during the processing. However, if you have small amount of residues remain, they are very easily to get oxidized during the subsequent storage, and those further oxidation will also result in generation of the Beany flavor. So the storage temperature is a key factor. The protein should be maintained at a low temperature to reduce the production of Beany flavor during the storage. The research demonstrated for pea seed kept at 22 or 37 degree had a higher aldehyde compared to those stored at a 40 degree. And also parameters like water activities or preservation of the protein in dark rather than exposed to light are also the strategies to improve the flavor of pea protein. And also the atmosphere modified packaging also play a role. For example, compared to vacuum packaging, if you have nitrogen filled in this packaging systems, you can more efficiently inhibit oxygen oxidation. That will delay the formation of Beany flavor component. In addition to volatile component, there are also some non-volatile organic component like saponin or polyphenols, they contribute to bitterness and astringency of the pea protein. I see the research publications demonstrate a breeding effort already there to remove the saponin and the polyphenols. But there are some considerations like saponin. It's a chemical barrier against the pathogens. So if we remove the saponin, whether the crop will be more prone to attacked by the pathogens. And currently, the research effort demonstrate that after removing of the saponin in pea, they still have good germination and protein content on the controlled greenhouse conditions. And the data group wanted to move this to their large field trial in the next step. And also, there are some work demonstrate that phenolic compounds can be removed by breeding work. However, the polyphenols, phenolic compounds, they are important source of antioxidants. So they are considered as health promoting component. So really there are some considerations. Shall we remove them or not? So then basically that's our discussion of the Beany flavor generation mechanisms, where they come from. And also we discussed some of the strategies to try to remove the Beany flavor. In my mind, we needed to have more breeding effort to have lipogenase-free pea genotypes. This has been demonstrated to have more successful in soya protein. Those technology can be used by pea work. And also, I think the combination of different processing technology for pre-treatment, after treatment can be combined together to have more efficient strategy to remove Beany flavor. Fermentation currently is effective to produce the food with Beany flavor efficiently removed. And at the same time, you can have hydrolyzed protein for better absorption. So that's the end of my presentation. I would like to thanks the funding support for my research programs, including federal government, provincial government, and industry partners. And then thanks everyone for your attention. If you have any questions, you can ask me by sending me email. I will be glad to answer those questions and discuss them with you.